Well, good morning everyone. Welcome to one concept per day problem, and the concept that we are currently learning here is about the specific heat. So in the earlier problem, we have already learnt about what is specific heat, how do you define that, and what happens if the temperature of a gas is being increased, okay, and we have reflected this based on the internal energy. And then we also looked at, okay, using first law of thermodynamics, how do you explain that there are two different specific heats, which is constant pressure and at constant volume. Okay, now let us look at the next part, which is the what is meant by temperature. And in this video, what we do is we look at a different way of looking at specific heat. So how do you interpret the data, okay, and how do you get the, or how do you calculate the specific heat using a temperature time graph? This is one thing which we'll be looking into. And then we also look at, okay, how do you understand what is the rate of loss? That is, it's not only about the specific heat, it's related to the energy also. So how do you calculate the power? What is rate of loss of energy? And after that, we look at what is, how do you calculate the latent heat of fusion? Okay, so with this we come to an end to the second video also. So anyway, let us continue with this now. Right, now explain what is meant by temperature of a substance. Okay, this question we have already addressed a similar question in one of our previous videos also, but anyway, let us redo it once again. So it is a measure of, it's a measure of the average kinetic energy of all the molecules in the gas. This question has been asked umpteen number of times, but still, okay, many of them make a mistake, but see to it that you measure these two terms, you mention these two terms, measure and average kinetic energy. Okay, measure of the average kinetic energy of all the molecules. Right, next one. This is a wonderful problem. The temperature is placed, a thermometer is placed in a liquid containing an open beaker. The reading of the thermometer is recorded at regular intervals. Okay, regular intervals. It means what? It's meaning it's recorded at something like 200 seconds, 400 seconds, 600 seconds, and so on. The variation with time t of the temperature is shown over here. Okay, how does the temperature vary? That's what has been shown. Now let us read the terms here. Temperature is measured in a liquid term contained in an open beaker, which means what? The lid is open, so the heat can escape to the environment. First thing, okay. The reading of thermometer is recorded. Okay, then next is temperature of the surrounding is 20 degrees centigrade. So you have a beaker, okay, and then there's a water filled until here. You are not going to heat this one here. So already at a given temperature. What was the initial temperature? Initial temperature was seen to be somewhere over here. How much is it? It's nearly 75. 75. It was initially at 75 degrees centigrade. And then you observe the outside temperature was 20 degrees centigrade. This was 75, this 20 degrees centigrade, and you have inserted the thermometer. You have inserted thermometer, and then you observe that the heat is being getting lost to the environment. On the graph, continue the line to show that the variation with time of the temperature of the next 3000 seconds. So what you are going to do? You are going to find out for the next 3000 seconds. Continue the line to show the variation with time of the temperature of the next 3000 seconds. For the next 3000 seconds, starting from here, okay, how is the variation being seen? So what will happen? So let me assume that this goes like this. So it will go like this over here. See here it is reducing. So this was at liquid. It says it's a liquid, it's not water. Okay, I made a mistake by saying it's water, it's not water, it's liquid, some other liquid. Why I'm saying this is because okay, the water, if it was water, it would have continued to be in a liquid state until at least 0 degrees centigrade. Okay, but here it is, see, it's not at 0 degrees centigrade. So therefore, it is until this 48 degrees centigrade, it is still liquid. Okay, so therefore, this is liquid. This is liquid to solid state. This is solid state over here. Now, what can happen over here? So this can, now it's already in the solid state. This can still go down for the next 3000 seconds. Right? It's already at 3000 here. Where is next 3000? It is 6000 here. 6000 is at this point. So therefore, sorry, 6000 here. And now whatever is the slope here, what is the slope that we get here? The slope here, let me find out. This slope is equal to how much? This is 48 for 8 degrees. 8 degrees in 1000 seconds. 8 degrees in 1000 seconds. Okay, if it is 8 degrees in 1000 seconds, then for 3000 seconds, it would be 24 degrees. That's what is the slope. So therefore, now from here, I should count for 24 degrees. How much is 24 degrees here? this is your 10 degrees, 20 degrees here, 22, 24. 24 should be here, and from here 3000 should be over here. So I should now extend this line until this point like this. Okay, we have got this line. Next. What does it say? And the graph continue the line to show the variation time of temperature for next 3000. Fine. By reference to the graph, state and explain the rate of loss of thermal energy from the substance between 0 and 600 seconds. 0 and 600. Between 0 and 600. 600 is somewhere over here. So what is happening between 0 and 600? That's what is the question. So explain the variation. What is the variation here? Rate, state and explain. Okay. So how is the what you call the temperature, or what is the, how is the energy getting released over here or reduced over here? You see. Okay. So first is, it's an open beaker, and then energy is lost to the surroundings. Energy is lost to the surroundings, and then you can also say that, what else can you see here? Energy is lost to the surroundings, and temperature is reducing. Instead of saying temperature is reducing, you can say temperature. Okay, temperature is reducing, and liquid, and the substance is in the liquid state. See, what is the expectation is that we need to look into the graph, understand what is the problem given, and then mention what is your observation. That's what we need. Okay, so we have got this between 600 and 1800 seconds. Now, which is the 600 and 1800 seconds? It's here. This is your 600, this is your 1800. So what is happening in this region? In this region, what's happening? So there is no decrease in temperature, which means what is the phase transition. So let us write down that. So for 4 mark, I need 4 pointers over here. First point is, there is a no change in temperature. Then second, what's happening? Phase transition from liquid to solid is seen, because the next state to liquid is nothing but solid only. You cannot have any intermediate state there, right? Okay. And then the third one, what else can be seen? Molecules. When something like this is happening, what can happen? Molecules move slower. And next, what else can happen? Then when molecules are moving slower, there's a bond creation between them, right? Bonds are created between them so that it becomes a solid. Even before this, if you want, you can write one more point. You can say the cohesive force is larger in this state, than in liquids. You can mention all this. Maybe still one more point also. You can also write potential energy of the molecules. Potential energy. What happens to potential energy? When it is farther away, it's higher. Potential energy of the molecules reduces, and so kinetic energy also reduces. Okay, you can mention all these points. Kinetic energy reduces. Kinetic energy does not reduce. Kinetic energy is constant. Kinetic energy is constant. You can mention all these points. Then use the graph. The mass of the liquid is given to you. Mass of the liquid is 0.11 kg, and the liquid and the specific heat capacity of liquid is 1300 joules per kg per Kelvin. Specific heat is equal to 1300 is given. In the graph, deduce that the rate of loss of thermal energy at time t equal to 600 seconds is approximately 4 watts. At time t equal to 600. So from the graph, we need to show you how to calculate this. Okay, that is too small. Let me just zoom into to get it correctly. Right. Now we need to find out what is the thermal energy at 600 seconds. 600 seconds is where? It's here. 1, 2, 3. This is 600 over here. This is 600 over here. So 600 is at this point. What I will do is, I'll just take at this point one division here. Okay, one division here, not even one division, half division I will take here, half division I will take. Okay, and I will find out what is this value. So I will just find out what is the slope here. What is the slope here? So delta t divided by delta t is your slope. Now what is your delta t? Delta t, I will take this as, what is this value? Is 600 seconds, right? 600, I will take this as 48 over here. This is not a problem. I'll take it here. It'll be fine. I'll take this point over here and this point. This will be fine. This is A, this is B, and this is C. What is AB here? AB is this is 52, 54, 54 minus 54 minus this is 48. 48 divided by, what is this value? Let us look at this value. Each division is 200. So therefore, see, I have taken this point and this point. So this is 200 over here. So only one box, small box I have taken. This should be 200. When I do this, it should be 6 divided by 200, which is 3 by 100, which is equal to 0.03 degrees Celsius per second. Okay, I have got this. Now, why do I need this? If you ask me this question, then I'll know that the energy which has been lost over here. What's the question over here? The question is, use the graph to reduce the rate of loss of thermal energy at time t equal to 600 seconds. It's approximately 4 watt. Okay, he is asking you to find out rate of energy loss. Now first what we do is, let us find out what is energy. How do you find energy? E is equal to mc delta t. This is your energy. Now if I want to find rate of energy loss, what should I do? When I say rate, you are also always going to divide this by time, right? So here also I am going to divide by time. Instead of writing time, I'll write this as delta t over here on both the sides. What is the delta t by delta t? That's what I have got from the graph over here, right? How much is it? 0.03. Let me substitute one by one. What is the mass of the gas that is being used over here? Mass of the gas was seen to be 0.11 kg. 0.11 kg multiplied by the value of C is already given, 1300, multiplied by delta t, which you got as 0.03, right? When I substitute all these values, let me see how much do I get. Okay, so I get 0.11 into 0.03 multiplied by 1300. I get the answer is 4.29. 4.3 watt, which is nearly equal to 4 watt. Okay, this is how we do it. So thus I can now reduce this. So I can say this is equal to 4 watt. How do we do? We found delta E divided by delta T, or E by delta T is equal to mc delta T by delta T, and we substituted all the values over here to give rise to 4 watt. Okay, this I got it from the slope. Okay, now let us move on to the next one. Calculate the specific latent heat of fusion of the liquid. Okay, a wonderful question to be noted down here. The reason is because, see, you may think, how do I calculate over here? What is specific latent heat of a liquid or a gas? Okay, so here it's a liquid, not even a gas. Okay, so how do I find it? Specific latent heat is given by m into L. Okay, there's no change in temperature. Anyway, that is not there. Now L is not known. So now what we need is, this is your energy E. So m into L is equal to E. L should be equal to energy by m. Now m is known anyway, 0.11 kg. What is this energy E? How do I know this? Okay, this is the question. So towards it, now what we see here is that power, see the rate at which the, what you call, the power gets reduced. Okay, the rate at which the energy is getting lost, whether the substance is in a solid state or in a liquid state, is always one and the same. Remember this always. Okay, the rate at which the energy is getting lost to the surroundings is always one and the same. So as a result of this, what you should do is, you should find out this energy what is being lost. In some cases, energy could be fastly lost. Some cases energy could be lost in a much slower way. but the rate at which it is losing is always the same. Okay, so therefore what I mean to say is that it is something like this. Okay, now what we do is see, let us say I have a fraction. Fraction is, let us say, 3 by 4. Okay, now numerator can be something like 8. Okay, but denominator should also be adjusted in such a way that the final fraction should be 3 by 4. So what will I write over here? If this is 8, so this should be, so how much can we write 8 here? No, I can't take 8, and maybe I'll take, okay, I'll choose it. Okay, let me take 8 by x is equal to 3 by 4. This is what it is. So therefore x should be equal to 4 into 8, 32 divided by 3. So therefore the value of x should be 32 by 3, so that you get the same answer. Okay, if you want a much more simpler answer, simpler way of explaining, maybe you can take something, let us say, for example, the numerator is 27. Okay, and denominator, I do not know how much it is, x over here. Okay, now this should always be equal to 3 by 4. So what should be the value of x? In 9 3s are 27, 9 4s are 36. If this value is equal to 36, then definitely it's the same. So this is similar to that of energy and time. Okay, which means what? In one of the cases, energy can be thrice. Okay, energy can be losing 3 joules, okay, in 4 seconds. Let's say in case of solids. In case of liquids, maybe it is losing 27 joules in 30 seconds, 36 seconds. But the rate at which it is getting lost is one and the same. Okay, but maybe liquid can lose more amount of energy, a solid can lose less amount of energy. That is possible. Okay, but while the ratio will always remain the same. Now, based on this, what do we have here? We have the energy by time is always equal to 4 watt. That we have already found out. Now we want to find out what is the energy lost over here. So how do we find? So what is the time here? The time here is seen to be 600 seconds. Now what is the time here? Time here is seen to be, come down here, time here is seen to be 1800 seconds. This is 600, this is 1800. What is the difference between these two? Difference between these two should be 1200. Let me write down, difference between these two should be 1200 seconds. Okay, so let me go back to my question. So I will write delta T is equal to 1200 seconds, in which the solid to liquid liquid to solid transition takes place. Okay, and then we also know that the power P is equal to 4 watt. So what is the energy which it is getting lost? The energy at which it is getting lost, E, is equal to power multiplied by time. How much is it? So I got 4 watt multiplied by 1200, which is equal to 4800 joules. This is the amount of energy the liquid is losing to become a solid, right? Okay, this is the value. Now we know that energy E is equal to M into M. Now things becomes easier. So what do we do here? So we'll substitute this 4800 here. This should be equal to 0.11 times L, or in other words, L should be equal to 4800 divided by 0.11, which should now be equal to, let me take up this, calculate this over here, 4800 divided by 0.11. When I do this, I get this is 43,636.3636 and so on. So what I can write is 43.6 or 43.4 kilojoules. 43.4 kilojoules per kg, because you do not have a temperature over there, you only have a mass over here. I can write 43.4 kilojoules. That is the right answer. 43.4 kilojoules. Okay, that's the right one. Okay, now let us move on to the next one. So with this, I think we have come to an end to this particular question, this video, and in the next video we will see how specific heat can be linked to resistance, power, current, and so on, all the electrical parameters.